Okay, so in this video lesson, let's look at the transformations on a graph of sine and a graph of cosine function. Okay, so let's put back the graph of the standard function y equals sine of x. And so the graph of sine of x is here, and for the rest of the video lesson today, I'm only gonna, for any of the graphs here, I'm gonna be doing that in only one period. And as you already know, sine and cosine functions, their graphs are the periodic, and so here we only do, once again, only one period. So this is the standard sine of x. It has and recall that the amplitude for this graph, it has the amplitude being 1. As for that vertical distance from the x-axis, or I also call that it's the center line, the midline from the x-axis here in the standard case to the high peak, and also the same space, the same vertical distance from the center line or the midline to the bottom peak of your sine of x function. And so that amplitude there, that height of the wave there, is being 1. And so that's what it means by the amplitude being 1. And that's just a couple review of the terminology. The period for our standard sine of x, once again, the start of your wave to the end of your wave takes the entire window, takes the entire interval from 0 to 2 pi. So that entire interval length, it's making up the period. So the period here is a total interval length of 2 pi. So like as I said again, this wave, this 1 unit wave right here starts at 0, x equals 0, and ends at x equals 2 pi. So the entire interval's length right here is referred to as the period. And that period, in our case of the standard sine of x function, the period is 2 pi. And other information, as I have already said briefly, but this function sine of x right here has a central line, being that line y equals 0. Or center line, sometimes also referred to, some textbooks also refer to that as the midline. And the line y equals 0, but here in the standard case it's really just the x-axis. So now I'm still going to leave my y equals sine of x here on my writing board. However, I'm going to put in a different function. So let's say this time we are going to see how the technology can quickly get us the graph for y equals sine of x. But this time I am going to add a value, let's say 1. So, and before I show on the graph, let's put down a list here. So for this new function, what is the amplitude going to be? After we see the graph, we're going to investigate the amplitude. We are going to investigate the period. We are going to investigate where do we find the center or the midline. Center line or midline. So these 3 important properties. Okay, so here on my, using my technology on my graphing, electronic graphing paper here with Desmos, then our sine of x plus 1 is here. and then to make it clear, I am going to also put the midline or the center line here. So any graph of sine or cosine will always have a midline, because the wave is going around that midline, up and down around a midline. And so observation here is telling us that it's the same shape. And let me also put back the original. So here my transform version. So here sine of x plus 1, I'm going to put that in a blue. And as a matter of fact, for the rest of the video lesson, anytime we apply a transformation on a graph, we are going to use a blue version. And I'm going to and the original version of the sine or cosine graph is going to be in red color. And so my original sine of x is here. So what is the relationship now? So it looks like the exact same shape of the sine function from the original sine function. All it happened in this sine of x plus 1, first of all, the midline is being pushed up from originally y equals 0 or the x-axis. Now it's being pushed up to y equals 1. So the midline here is y equals 1. And then for that reason, and it looks like our eyes can tell us that the entire original graph, which was in red version, now the same graph but being in blue version, the wave up and down around that center line is now being brought up or being pushed up 1 unit. So the high peaks happen at 2 and the bottom peak happens at 0. And so in the end, the amplitude, the wave height, the height of your peak right here is still going to be just 1 right after from observation. So the amplitude is 1. And the period, once again, my wave here, simply what we see here is simply just the exact wave being pushed up vertically up. And so start is here at x equals 0 and y and end is here at x equals 2 pi. So we're still going to have a total intervals length, a period interval being a 2 pi distance, a 2 pi period. And so the period here is 2 pi. So the only difference here is, so we have y equals sine of x plus 1, and the only difference with the original function here is that we're adding a constant 1, a positive constant 1 to the original function. So now the midline or the center line being shifted up, and so for that reason, consequently, the entire sine function, that original sine function being pushed up 1 unit, being shifted up 1 unit. And so before we move on too far here, let's quickly, I'm going to use my animation here on my graphing, my electronic Desmos graphing right here. And I'm going to quickly switch to different values so that you can also investigate and enhance and strengthen your understanding in terms of what happens if we subtract a value. So here I'm going to go ahead and do an animation, and you can see that my graph this time is being moved down, and this time how about let's purposely stop at right there where that center line is at -1. And so after the animation stops right here, and it's clearly we're looking at the center line being at y equals -1 according to the graph from observation, and it looks like the whole shape remains the same here. It's mainly that wave again, and it waves up, it waves down, and then so the wave height remains the same, being 1 up and being 1 down. So the amplitude here is 1 again. And the period of this wave after the animation is the starting still again, x equals 0. And the ending of the wave is when x equals 2 pi on the x-axis. And so the total window here, the total intervals length here is going to be a 2 pi. The math here is going on, the math that was going on here is 2 pi. The ending point, subtract x equals 0 for the starting point, that gives us the total intervals length right here. So in this case, our period, which is a different name for the intervals length, the period interval, 2 pi. And that was our function. So the same shape remains. So that must be the sine of x. And the same shape consequently brought up, the amplitude has to be the same, and the interval has to be the same. But this time, since the animation showed that we stopped the animation by moving down to the center line, to be around the center line y equals -1, so my graph here has to be sine of x minus 1. And so that's, I purposely approach this way for this little example here, so that you can see that sometimes that's how we recognize what transformation is happening in a particular graph. So now, generally speaking, when our function here is a sine function, starting out with a sine function, and we add with a constant, and provided that our constant is a positive constant, let's assume that we're only working with positive constant, then a function like that we have seen throughout our demonstration animation, or our demonstration example, then the center line is being located at the line y equals c. And so, and the periods remain the same, being a 2 pi period window, and the amplitude is the same, being 1. Or in the term that we used to use back in pre-calculus 1, then the graph here, the graph for the function like this, shifts c unit vertically upward. That's why I'm drawing the arrow pointing upward like that. And then we also saw that when we subtract from the sine function a constant c, and once again stay in that assumption, stay in that convention that we keep c being a positive constant, and so subtracting a positive constant, what we've seen in our latest demonstration, then the center line is being located at y equals -c here. And the period, since the function remains the exact same graph with the sine function as we have seen back in our demonstration, then the period remains exactly 2 pi, and the amplitude equals 1, the height of the wave. And so in common language, as we used to use back in pre-calculus 1, we say that this graph shifts the original sine of x graph here shifts c units vertically down, and that's why I'm using that arrow that's pointing vertically down like that. Let's now have a look at the cosine function. And so before we can start any further, let's look at the standard cosine of x function in simply one period. So in one period, the cosine function's graph looks as following. And so now, once again, it's a waveform, but we only bring it down into within one period. And so, observing this graph right here, you can see once again you got a bottom peak, and we have two other high peaks right here. But it looks like there's a center line, or some textbook refer to that as the midline. And from where the center line or the midline, that's distance, that vertical distance to the high peak, or once again from the center line down to the bottom peak, that's the amplitude of your cosine wave. And so, very similar to the sine function, cosine's graph has the amplitude. So on this particular standard cosine function, then the amplitude equals 1. So positive or negative is just simply indicating where the peak is heading. So if the peak is a positive peak, being positive 1, or it could be negative 1, but here the amplitude is strictly just the absolute amount, the absolute value of the peak. So it's either the peak is pointing up or the peak is pointing down. It's having the wave itself is having amplitude 1. Period of this short segment of wave right here. This wave of cosine starts at this dotted line right here, x equals 0, and this other line, x equals 2 pi. So one period happened between this interval, and we refer to that as one period of the cosine, as you already have seen that in your basic understanding of cosine graph right here. And so the total length, once again, the total length from the start to the end of your period interval, that's the period, how long that is. So this interval here is a 2 pi length here. So in other words, the period for your cosine function is a 2 pi period. And then this cosine function, the standard cosine function, has center line, or some textbooks refer to that as the midline, which is that line y equals 0, or the x-axis again. And that line is right here, the x-axis, or the line y equals 0. And now we are going to investigate the graph of cosine of x, but plus with a constant 2. So on my Desmos graphing calculator, I'm still going to leave the original standard cosine of x here, and I am going to put the graph of cosine of x plus 2 in blue, so that we can see and make comparison and draw out how adding a constant to your cosine of x function will cause that change, will cause that transformation, how the transformation will happen. And so now, here's our function cosine of x plus 2 is here. And to make it clear, I'm going to also put the center line so that we can recognize it more clearly. So as far as amplitude, and once I put the center line up, then the amplitude is clearly found to be, once again, from where the center line is, reaching up to the high peak, and from where the center line is reaching down to the bottom peak right here. That space, that distance, that vertical distance remains 1. So now on this particular new function, y equals cosine of x plus 2, we're concluding that the amplitude is still 1. What about the period? So even though it's cosine of x plus 2, but if we're looking at our graphing device here on Desmos, this wave in blue still start at we're still having the same start with the original cosine function in red here, and further it has the same ending with the red original cosine. So once again, the red color of mine here is the original cosine, and the blue one is the cosine after the transformation add 2. So cosine of x plus 2 is here. And so I'm going to put up a vertical dotted line for the start, and I'm putting up another vertical dotted line for the ending. So my cosine of x plus 2 is still in between that interval from 0 to 2 pi. And so that means my period of this blue cosine of x plus 2, blue cosine of x plus 2 is going to be period 2 pi, because the total length of that interval is 2 pi. And apparently, let me clear away the start and the end of our wave here so that it only shows the center line is here. So the last piece of information, the center line is located at the line y equals 2. And so it looks like what this transformation did to the function cosine of x. So from where the original function is, it brought that adding 2 to the original cosine of x is going to bring the center line 2 units up. So this is up, or heading up arrow by 2. And more, it's easier to narrow our attention down by simply focus on the center line right here, the center line or the midline. The midline is being located now at y equals 2. That line right here, y equals 2. And so now after this, let's go ahead and investigate another one. So once again, I am going to make an animation, purposely leaving my red original cosine of x function is here, and I'm going to animate my blue cosine of x plus c here up and down so that you can see and understand more clear. So now I'm going to adjust my center line, and you can see that my blue cosine graph is being brought down accordingly. So how about I'm going to move it down to and pay attention to the center line. So how about let's leave the center line right there at y equals -1. So let's make a good guess on what that graph is. Let's make a good judgment of what that function's equation is. It's going to have to be y equals cosine of x. Notice the reason I know this, because the amplitude from where the center line out to each peak right here is still 1. So the amplitude is still 1. The total interval from the start to the end of this wave, this 1 unit of wave, is still that length being a 2 pi length. So the period on this wave remains the same compared to the original version, and also compared to the earlier version that we did. And so it must be having that cosine of x function. But then the center line this time, after the animation, stops at y equals -1. So in that way, my function, the equation for this function here is clearly cosine of x -1. And so that's how we recognize the function, and that's how we can understand how the function, how the adding or subtracting a constant affects the graph of a function. And specifically in this example, I'm doing cosine function. So generally speaking, when our function is a cosine of x plus with a constant c, assuming c is a positive constant, then what we have found throughout our investigation is that the amplitude remains the same, being 1. The period remains the same as the original standard cosine of x, 2 pi. The center line now is being located at y equals c. That's horizontal line y equals c. So another way of understanding this, when we add a positive constant to our cosine wave, then doing this will bring or will shift our graph vertically up by c units. And then it's easy to understand that when our function is cosine of x, but minus a positive constant c, so assuming c is a positive constant, then what it does, it's going to shift the graph vertically downward by c units. And of course, the amplitude of the cosine wave remains the same, 1, just like the original standard cosine. The period, once again, remains the same, being 2 pi. However, the center line is being brought down to y equals -c. And so generally, let f of x be either a sine or cosine function. Then if we're adding a positive constant to either your sine or cosine function, then what's happening here is that the amplitude won't change and remains the same, being 1 compared to the original standard amplitude. The period also remains the same as the original standard sine or cosine function, being 2 pi. But the center line or some text will call that the midline is at the line, the horizontal line y equals c, and for now c has a positive value. And so we can generally regard to this as we shift our original sine or cosine function vertically up by c units. And similarly, if our function is either a sine function or a cosine of x function, and we are subtracting from our function f of x a constant c, assuming again that c is a positive constant, then the transform graph here is going to have the same amplitude as the original either sine or cosine, having amplitude 1, period here being 2 pi, just exactly the same as the original standard sine or cosine. But the center line this time is going to be at that horizontal line y equals negative c. And we can think of this as subtracting a positive constant from our trig function, either sine or cosine, is going to shift our graph vertically downward by c units. So that's a conclusion regarding our sine function, adding or subtract a constant. Alright, so once again, here's our sine function, the original sine, the original standard sine of x function, and here's its graph on my Desmos graphing calculator. And once again, we only need to focus on one basic period. So there's that nice sine wave. Once again, the amplitude equals 1 for the original sine of x. The period equals 2 pi for the original standard sine of x. And the center line for this sine of x is y equals 0, as a reminder. And now, still leaving the sine of x being on my graphing calculator, my graphing device here, I am now going to put the graph of the function y equals 2 sine of x together with our original sine of x function, so that we can investigate what has changed and how this new function is being compared to our original function sine of x. And what we notice here is that we have a coefficient positive 2 multiplied in front of our sine of x here. And so, still having my original sine of x being here, my function 2 sine of x is now being in blue. So, fundamentally, it still carries that same exact shape. There's a wave going up first, and then it crosses through the x-axis, and wave down, and then come back to the center line. And there's once again still that center line here. So, it looks like, as far as the basic information, it looks like the amplitude, the height of the wave this time, is being twice as high. So look at, and compare with the original red sine of x right here, then our blue version 2 sine of x now is having the amplitude being twice as high. So the wave height, or that vertical space from the center line out to the upper peak, and that vertical space from the center line down to the bottom peak being as far as 2, twice as far as the red graph right here. And so we can now say that the amplitude here in this case equals 2. And the period, it looks like two versions, the red original sine of x and the blue 2 sine of x. They all have the same start and ending at the same end right here. And to make it clear, I'm really gonna put it up the start and the end of our basic units graph right here. But it starts at x equals 2 and it ends at x equals 2 pi. So in the end, the entire period interval here, the entire interval from start to end, is our period of the wave is being 2 pi again. And so, and center line. For this sine, center line for 2 sine of x is exactly the same with the center line for the original sine of x. So located at y equals 0, or namely the x-axis. Also called the midline. And now I am going to investigate another one. Let's say y equals 1/2 sine of x, and allow me to do a little animation. So our red curve here is the original sine of x function, and our other curve being in blue here is from the previous example, which was the positive 2 sine of x function. So you can see that the amplitude for this wave, the wave height here, is hitting as high as 2 or as low as -2. But now I am going to animate by letting the wave get smaller, and now when it's 1/2, it lands about right here. So this is where we have our blue wave this time is having the amplitude, a different amplitude here. So the amplitude for 1/2 sine of x is now looks like being only a 1/2, and the period remains the same from observing our graph here in blue, so being a 2 pi, and the center line remains the same again, being that line y equals 0. What about if we put a negative coefficient in front of our sine function? So let's say -2 times sine of x. And here's our blue version. And so it looks like we're still having that wave, but this time the fascinating nature here is the wave being flipped upside down and right around the x-axis, that center line here, right around that center line, y equals 0. So drawing out some observation from that, amplitude, the wave height remains, the wave height in this case investigated to be 2. So as we have done about 3 little problems here on this type of problem so far, then you start noticing how the amplitude being changed as I keep changing to different coefficient value in front of our sine function. And later on we're going to navigate over and work over with cosine, and we're going to even find a better generality. In my current graph right here, both the blue and the red are having the same period window, same period interval. So the period here, the interval's length there, where it starts and where it ends, remains 2 pi compared to the original red graph. And the center line. And the center line here is being at y equals 0, the x-axis. But make a note for ourselves. The graph this time, compared to the earlier two cases, and the graph is flipped or reflected around the x-axis for that line y equals 0. And keep in mind the x-axis in our problem here for now is think of that as the center line or the line y equals 0. So that's one additional note we made when our coefficient in front of the trig function being a negative number. So here's the generality about what we have investigated so far. Starting out with our function being a sine function, our trig function being sine of x. But what we did here throughout our investigation was we multiply with a coefficient m in front of that. And keep in mind here, we tried when m was being a positive number and when m being a negative number, and we saw some changes to the graph. And so it looked like, as a generality here, then the amplitude of our wave, the amplitude of our sine of x function related to the coefficient m here by taking the absolute value of m, because m could be a negative value itself, but being a negative can graphically can physically affect the shape by flipping it upside down, and I'll talk about that a little bit later. But for now, as far as the amplitude, the wave height, how far it is out from the center line out to either way, one of the upper peak or the bottom peak, the amplitude is being the absolute distance, the absolute vertical distance right here. So absolute value of m. The period remains the same with the original sine of x function. So it's still a 2 pi. And here the center line is being at y equals 0. And so now back to this general form right here, when we have a coefficient multiplied with our trig function sine of x right here, then as a further detail here is that when our coefficient m being specifically negative, then besides having the amplitude being absolute value of m, we're going to have our graph is reflected through the x-axis. And I highly encourage to understand the x-axis here as a generality, the center line. So generally speaking, anytime our m value is being below 0, being negative, our graph is going to be reflected through the center line of our trig function, of our trig graph. Cosine function originally has this graph being this curve right here, this shape right here. And we already knew that the original standard cosine of x has amplitude 1, period being 2 pi, start of the interval is here, and ending of the interval at 2 pi, start at x equals 0. And then the center line is on the x-axis, or y equals 0. So that was the original standard cosine of x. In the same space with the original cosine of x. Let's now graph the function y equals positive 2 cosine of x to see how the transformation is being applied to the original cosine of x function by simply multiplying the cosine of x function with a coefficient positive 2 here. So notice this is a positive 2 coefficient being multiplied to the function cosine of x. So this is once again the graph of the original cosine of x. Our graph of the function 2 cosine of x is going to be the curve in blue. Now, after the curve in blue being brought up for here and being graphed together with the red curve, so the red curve is for the original cosine, and this curve right here in blue is 2 positive 2 cosine of x. And so now let's have some observation here at the curve. So primarily speaking, both the red and the blue curves are having the same fundamental shape again. We have a starting out at a peak, it crossed through at the quarter point, and it hit the bottom peak here in the middle, and then end at another peak right here. So fundamentally the shape looks exactly the same, but it seems like the function in blue right here has the wave height being twice as large compared to the wave height of the red curve. And so after that observation, we can now make some quick little, we can note our little observation here. Amplitude of this function, 2 cosine of x. Amplitude is being changed to 2, positive 2. The period, allow me to put in the start and the end of the interval of the period intervals, so we can see clearly the period of the basic units of our cosine function right here. So period here is 2 pi. As we can see from the graph here that our blue curve starts at x equals 0 and ends at x equals 2 pi. So the period here is a 2 pi period, the total intervals of the total interval length right here. The center line of our blue curve is the same as the center line of the red curve, so it's being y equals 0 or the x-axis. I'm going to do another little animation to bring our graph in blue to land at this function 1/2 cosine of x. So with my decimal graphing calculator, I am now going to animate by bringing my m values differently. So here I'm going to change my m value. So now I'm changing, and now as I hit to 0.5, which is 1/2, and look at how it changed the shape of my blue curve. So my blue curve here is now, this blue curve is the curve for 1/2 cosine of x. Let's start observing here, but fundamentally again, the shape is the same as the red curve for original cosine of x, but now the wave height is only 1/2 compared to the original red curve. And so now we conclude that when our function is a 1/2 with coefficient positive 1/2 multiplied with the original cosine, then our amplitude is changed to 1/2. Our period, it looks like the period interval remains with the same start and the same ending right here. So we have a total interval's length for the period being 2 pi, as it started, as our blue curve started at x equals 0 and ended at x equals 2 pi. Our center line also remains the same again, being the x-axis or the equation y equals 0. And now let's quickly investigate what's the graph of -2 cosine of x. So apparently this is the original cosine and multiplied with a negative coefficient 2. So on my graph here, this red line this red curve is the curve for the original cosine. Now minus 2 cosine of x is here. So it looks like that fundamental shape is still here, but this time it's got flipped upside down, or more formally, it's reflected through the x-axis due to the negative coefficient 2 in front of the cosine function. And it's still in the end a wave. So wave height is being, and looking at the grid here, it seems like wave height is being at 2 here. And so for this wave, the amplitude is observed to be 2. The period, once again, this piece of curve in blue has the same starting with the curve in red, and also has the same ending with the curve in red right here. So it starts at x equals 0 and it ends at x equals 2 pi. So our total period interval, or total period window, is 2 pi. And our center line is still the same as with the original cosine function, y equals 0, or in other words, the x-axis. And so now we can form another generality regarding our cosine function of x, but having a some coefficient multiplied in front of the cosine of x function. So noted that the coefficient m can be positive or it can be negative. And so, and throughout our investigations, it looks like the amplitude is being changed by the absolute value of m. So the amplitude of this function, coefficient m times cosine of x, the amplitude will be equals to the absolute value of coefficient m. The period is going to be the same as the period of the original function, cosine of x, which is 2 pi. And the center line is also the same with the original function. And keep reminding yourself, center line is the same as a midline. And the center line is the x-axis, or the line y equals 0. And in case another further notes, further details, that when m is a negative coefficient, then the graph is reflected through the x-axis. In the context of trig function, I prefer that to understand that as the center line of your wave. So now, generally speaking, when your function is either a sine function, sine of x function, or a cosine of x function, and there is a coefficient m being multiplied in front of each of our trig function here, then generally speaking, it's going to generate a graph, a wave with amplitude. We have seen through our investigation that the amplitude on any of these graphs here is going to be the absolute value of m, the coefficient, and the period going to be 2 pi, the same as a standard original sine or cosine. And the center line is on the x-axis, or at the line y equals 0. Center line is also referred as the midline. And a special note as well, that when our coefficient m is being a negative value, then the graph. And in that case, the graph is reflected. To x-axis, or generally in the concept of trig function, we call it it's a center line.